Hello once again, this is Mr. Donahue here, taking a look at pre-nuclear review. So basically all the stuff that we should remember before we get into nuclear chemistry. So let's start with the history of the atom, the evolution of the model of the atom, and the experiment. So first model was the Dalton model, where it just looked like a hard sphere. Now, how did we come to determine that that's what atoms are like? Well, the thought experiment. They just thought about it. You can cut something in half a bunch of times. Eventually, you're going to get down to something that you can't cut in half anymore, and that's going to be indivisible. And the word for indivisible in Greek is like atomos, so that's how we got the atom. It's just a hard, solid sphere. It looks like a billiard ball. Then Thomson had an experiment where they discovered that there was positive and negative charged particles in an atom. So that's the plum pudding model, which, you know, I think of chocolate chip cookies because I'm not British. I don't know about plum pudding, but basically it looks like a sphere, and it's a positive sphere, and in that positive sphere there are negative chocolate chips, if you will. So that's what the Thomson looks like. Rutherford came along, did the gold foil experiment, and in the gold foil experiment they determined that most of the atom was actually empty space. You had this positive, small but dense nucleus, and then you had the electrons somewhere on the outside. Now Bohr came along and saw the bright line spectra, and figured out that, well, these electrons aren't just all willy-nilly like outside of the nucleus, that they are in distinct energy states. So we have a small positive nucleus, which is the same, but we have these energy levels. So that was Bohr's major contribution, is that there is energy levels. Then we discovered quantum math and all that stuff, quantum mechanics, and we had determined that, hey, actually these electrons don't behave just like particles. They also have a wave function to them. So we still have this positive charged nucleus, but the electrons are described as an area of probability. So energy levels are really just an area of probability where electrons will be found. And yeah, so that is the long and short of the history of the atom. All right, so structure of the atom. In the nucleus, we got protons, which can be abbreviated as a P, with a charge of 1 and a mass of 1. So charge is positive 1, and the mass is 1 as well. Neutrons are also found in the nucleus, except they have no charge. They're neutral, but they also have a mass of 1. And outside of the nucleus, we have the electrons. So the electrons have a charge of negative 1, and their mass is so tiny that we just say it's 0. You need something like more than 1,800 electrons to equal the mass of 1 proton. So we say it's so small that you can just say it's 0. It's almost 0. For everything that we do, it won't matter. We can just assume it's 0. So yeah. So isotopes. Iso means the same, and tope means, I don't know, element, right? So we have the same element. But what's different about them then? They have different masses. So if I was taking a look at, maybe I want to take a look at carbon with a mass of 12. Well, it has 6 protons and it has 6 neutrons. That's how we get a mass of 12. Whereas carbon-14, same element, so they have the same number of protons, because that's what defines the element, 6 protons. But how did we get a mass of 14? Well, this one had 8 neutrons, and that's why they got different masses. All right, so isotopic notation. Basically, there's a couple of ways you can write it. Right here, this is the atomic number, right? It's also the nuclear charge, because in the nucleus, the only thing that has a charge are the number of protons. So it's the number of protons, right? Up here is the mass, and the mass is from the protons and the neutrons. So there's two ways that we can write different isotopes. We can write it just like this, or we can also, shorthand, just go C-12, because that's the element, which tells us how many protons there are, and then this 12 is just telling us the mass. So it tells us which isotope we're talking about. All right, electron configurations. So if I had, I don't know, what's a good one? I'll stick with carbon. 6 protons and 6 neutrons. I also have 6 electrons. So I'm going to have an electron, 2 in the first energy level. I'm going to have 1, 2, 3, and 4 electrons in the outer level. So this configuration is 2-4. There's 2 in the first energy level, and there are 4 in the second energy level, or principal. Oh, that should be a P. second principal energy level. All right, so if I had something else like nitrogen, nitrogen has 7 protons and let's say 7 neutrons. There are different isotopes. So nitrogen, well, let's see, we have 1, 2, and then we're going to have 5 electrons on the outside. So its configuration would be 2-5. So that's electron configurations. Our production of light. Light's produced when electrons are moving between different energy levels. So we have the ground state, which is the default state for electrons, and they have the lowest energy. So let's say I just had 1 electron. I'm gonna say that this is just an atom of hydrogen. 1 proton, 1 electron. The excited state. So energy is absorbed by the electron and it bumps it up to a higher level. Just like this. This is my electron. It absorbs some energy. It gets bumped up to a higher energy level. This is the excited state. It's got extra energy. Now, when that electron gives off that extra energy and falls back down to the lower energy level, back down to the ground state, it gives off light. So light is emitted when the excited electron gives off the extra energy and falls back down to a lower energy level. And that's how light's made. Our Lewis dot diagram. So if we got fluorine, its electron configuration is 2-7. When we're doing these Lewis dot diagrams, we're only interested in the valence electrons. So what are these valence electrons? They're the last and outermost number of electrons. So you just go, all right, write the symbol for the element, and then you draw 7 dots around it because it's got 7 valence electrons. And the way that you number these dots, if this is my general element, first electron, second electron, and then you go third, fourth, fifth, sixth, seventh, and then eighth. So if I have fluorine with 7, I'm going to go 1, 2, 3, 4, 5, 6, 7. And that is the Lewis dot diagram for fluorine. For sodium, well, let's take a look. It's only got 1 valence electron, so boom, 1 dot over it. Nitrogen, 2-5. All right, well, N is for nitrogen. I got 5 valence electrons, so I go 1, 2, 3, 4, 5. And that is my Lewis dot diagram for nitrogen. All right, weighted average atomic mass. Going to do some math here. So an average mass needs to account for the abundance of all the different isotopes. For example, if we were taking the age of a class of seniors, all right, in my classroom, there are 17-year-olds and there's 18-year-olds. The average isn't going to be 17 and a half, right? I have to account for how many there are of each age. So if I had 20 17-year-olds and 10 18-year-olds, if I wanted to find the average, I would do, all right, 17 times 20, because there's 20 of them, and then 18 times 10, because there's 10 18-year-olds. I add them together and divide by 30, and that's going to give you your average age. We got to do the same thing for atoms. We don't count individual atoms because we can't count something so tiny. Like, it's not feasible. It's not going to work. Instead, we can figure out their percent abundance, which is easier to get, and we use that in our math. So the weighted average atomic mass is going to be the percent of the first isotope times the mass of the first isotope, then parentheses, bracket that, plus the percent of the second isotope times the mass of the second isotope, bracket that, add those together and divide by 100. So in the average age example, we divided by 30 because there was a total of 30 students. When we are doing percentages, we got to divide by 100 because the percentage is out of 100. So let's take a look at an example math problem. It says calculate the weighted average atomic mass for carbon based on the following data. So we're trying to get the weighted average atomic mass. So I got to take the mass of isotope 1, that's 12.000, etc., times the percent, 98.90, bracket that, add it to the mass of the second isotope, 13.003355, times by the percent abundance of that. And then this whole thing, I have to divide by 100 because it's a percent. And when I do that and I plug it in, I should get 12.011. It's going to be atomic mass units or grams per mole. And that is my weighted average atomic mass for carbon. Now, here's another example. It's for magnesium, and you see we have 3 different isotopes. So we should have 3 sets of brackets when we do our math. So that's all it is. Look, I'll show you what I mean. So the weighted average atomic mass is going to equal the mass of the first one, so 23.985 0.5042 times the percent abundance, 78.99, bracket that, plus second isotope, 24.985837 times the percent abundance of that one, which is 10, plus, all right, third isotope. I have 3 isotopes, I have 3 sets of brackets. The mass of 25.982593 times 11.01. Now all of that is going to get added together, and then I'm going to divide that whole thing by 100 because we're working with percents, and we end up with a mass of 24.305 grams per mole. And yeah, that's it. So I hope you found that helpful. I'll see you in class. Try the practice problems. Okay, bye.